to simplify radicals, we've done this before, but we're going to kind of go into it a little bit more and expand on it just a little bit more. So there's a couple of things to note, that if I have a to the nth power is equal to b, with a and b being real numbers and n a positive integer, then a is what's called an nth root of b. So we actually have and can take the root of the other side of the equation, and we take what is called the nth root. So for example, if it's squared, then we would take the square root. A couple of things to note. If n is odd and a is negative, then b will also be negative. If n is even and a is negative, then b will be positive. But the nth root of b will not exist, and I'll show you what I mean by that in a second, okay? So let's just take numbers and put this with numbers. Negative 2 to the third power is equal to negative 8, because it's negative 2 times negative 2 times negative 2. So it stays negative. So that's what I meant by b will also be negative. But here's the thing. Let's say I wanted to go backwards. So let's say I wanted to take the nth root of b. Okay, if I wanted to take the third root of that negative 8, then it can go backwards because it is an odd exponent. But over here, if I have negative 2 to the second power, that's going to be positive 4. But we cannot say that negative 2 is equal to the square root of 4. Okay, so the nth root, which is that square root, would not exist. So this actually does not exist. So it's okay if the negative, if we're like working backwards, it's okay to work backwards with odd exponents, but it's not okay to work backwards with even exponents, is what I'm trying to state. And we'll talk more about that later in another lesson, in another video. But I really today want to talk about what your radical is going to look like. So we have a radical, and this is what it looks like. It's the nth root of a. N represents the index, and a represents the radicand. So whatever the radicand is, and whatever the index is, they kind of go hand in hand together, and we can simplify like square roots and cube roots and all the things that we've done before. Now we're going to do numbers for now, and then we're going to add in the variables. But for example, let's say that I want to simplify the square root of 20. Now here's the thing. I know it's a square root because it's understood that if it is not written, that n is 2. So now that means we're looking for 2 of a kind. We're looking for perfect squares. And if that's the case, the best way to simplify these are with a factor tree. So you break it down to its prime factors and its prime numbers. So 2 and 10 multiplied to 20. Well, 2 is a prime number, so I'm going to circle it. 10 can be split to 2 and 5. So these are called prime factorization, is when we find all the prime numbers and we list them in order. 2 times 2 times 5. Now, when you have an exponent, or not an exponent, in this case an index of 2, that means we're looking for 2 of a kind. So I have a pair of 2's right here. To simplify this radical, I take the one of the 2's out, and then I leave whatever is underneath, or whatever is left over, underneath the radicand, or what underneath the radical, which is the radicand. So this square root of 20 simplifies to 2 square root of 5. Let's look at another one. Let's say I have the square root of 108. So we break down 108. When I did this, I said that it was 9 times 12. 9 is not a perfect square, or not a prime number, so we're going to break 9 down to 3 times 3. Now we've done this once before, but we're kind of going a little bit more in depth into it today. We're going to go a little bit more in depth into the whole thing. 12 is 3 and 4. 3 and 2. So when we list this, I list them in order: 2 times 2 times 3 times 3 times 3. And we circle pairs. So wherever I have a pair, I have 2 of a kind here because my index is 2, and I have a pair here. So wherever you have your pairs, those are your perfect squares. Now we pull 1 from the first pair out, 1 from the second pair out, and we leave underneath what is not circled. Now, what happens to those numbers out front? We multiply them together, giving us 6 square root of 3 as my final answer. So we've done this before. Okay, we've done this before. And what happens when you have a cube or something different than a square. So let's say I have the cube root of 108, just to see the difference. So you're still going to break it down to its prime factorization. That's 9 and 12, 3 and 3, we circle the 3's, 3 and 4, circle the 3, and then 2 and 2, circle the 2's. So I circle all my prime numbers so that I don't forget them when I list them. 2 times 2 times 3 times 3 times 3. The difference though now is instead of circling pairs, we're going to circle 3 in groups of 3 because now that's my index now. So if I have a group of 3, those get circled. Once again, we pull 1 from the group of 3 out, and then we leave underneath the radical with that same index whatever is left. So whatever is left over is 2 times 2, which is 4. And that's it. That's the only difference with the cube root versus the square root. Let's look at a different one. Let's look at the fourth root. Let's say I have the fourth root of 6,480. We're going to get big numbers here. Take a minute and see if you can break this down into its prime factorization. Okay, so what I did is I said I went with 80 and 81. 80 times 81, but you can use any two numbers that multiply to 6,480, any two numbers. I just chose 80 and 81 because I tried it out and it worked, so it just happened to go into my favor. So for the second group, breaking down 80, I did 8 and 10. To break down 8 was 2 and 4, 2 being a prime number. To break down 4 was 2 and 2, both again prime numbers, so I circled them. Then we have to break down 10. 10 breaks down to 2 times 5. 2 is a prime number, 5 is a prime number. So that's 80. So let's break down 81. That's 9 times 9. And then 9 is 3 times 3, both prime numbers, running out of room. And the other 9 is also 3 times 3. So now if I list this, I have 2 times 2 times 2 times 2 times 3 times 3 times 3 times 3 times 5. So I have 4 2's, 4 3's, and 1 5. Now I'm going to circle my index. Number of numbers that I need is in my index. I need 4 of a kind. I have 4 of a kind here. I have 4 of a kind here. I'm going to take 1 from the group of this first group, 1 from this second group, and then I'm going to leave underneath the fourth root whatever is left outside of the circles. So this becomes 6, fourth root of 5. Now that is how you simplify using just the numbers, but we are actually going to face a different challenge today, and that's going to do like what we do with variables as well. So we're going to go over to our next page, and we're going to go over a ton of examples with what to do with the variables as well as the numbers. So that's just the numbers, okay? Now, really quickly, before we go on, if I have a negative 8, this is 2 times 4 times 2. We're going to simplify this one. So I'm going to do 2, 2, 2, and I have 3 2's. So I know that this actually simplifies to 2 because I have 3 groups of 2. But this is going to stay negative because it's an odd index. So this happens in an odd index. Your answer will just be negative. Here's the problem. If your index is even in any of your problems from here on out, then you can't do it. It does not exist. Okay? And the reason is because if I were to work backwards to get to negative 8, I have to multiply negative 2 times negative 2 times negative 2. That works. But if I were to take negative 1 and work backwards, negative 1 times negative 1 times negative 1 times negative 1 does not equal negative 1. It equals a positive 1. So therefore, it doesn't work. Okay? So just make sure that if you have an even index, if my index is even and it's negative, that you automatically just go ahead and say it does not exist, because that is part of the property from the beginning that we were talking about. You can't work backwards for that. And all radicals need to be able to work forwards and backwards with my exponents. We need to be able to go back to my problem by multiplication. Okay, so let's add in those variables. Example, the square root of 16x to the 8th. So here's what I'm going to do. The first thing we're going to do is we're going to write out and do our number. Same thing that we were doing before. 16 is 4 times 4. That's 2 times 2. Circle both of those. And 4 is 2 times 2 again. Could have also used 2 and 8. It doesn't matter. So I'm going to write this out. That's 2 times 2 times 2 times 2. But I'm also going to write out the x's just to show you what happens, okay? So this is x times 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 x. I should have 8 x's. 1, 2, 3, 4, 5, 6, 7, and 8. Now, because it's a square root, I'm going to circle pairs. Well, look at my pairs. I'm going to circle the pairs of the 2's, bring 1 from each pair out. But I'm also going to circle the pairs of x's. I have 2 x's here, 2 x's here, 2 x's here, and 2 x's here. It's the same process. You're going to bring 1 from each group out. And then we multiply all these numbers together. Now, there is nothing left under the radical because I have nothing uncircled, okay? So in this case, I have 4x to the, how many x's? 4 of them. So it's 4x to the 4th power. So this is how I simplify this. However, it's not the only way to do it. And it's not the best way to do it. Writing it out works nicely for problems that are like fewer than maybe 10 exponent-wise. But if your exponent is 32, then this might, you're not going to want to write out 32 x's. So one way to look at this is to instead divide our exponent. So take our exponent that's inside the radical, so in our case exponent is 8, and divide it by our index. And our index in this case was 2. That should give me 4. That means for that variable, the exponent should be 4. So just a really quick recap, let's say I have the square root of x to the 32nd, okay? I'm going to take my exponent, which is 32, and divide it by 2. That's going to give me 16. So my x should be to the 16th power. And that's how you simplify it. Now, anything that's left over gets left underneath. So this is the only tricky part of this. So let's say it's a square root again, but it's x to the 5th power instead. Well, 5 and divided by 2 doesn't work. But it does work, like 4 divided by 2 does work. So you go to the next highest number. But we're going to have 1 left over. So what happens with that 1 left over? Well, we would take that 4 divided by 2. 2 goes into 5 4 times, or not 4 times, but 2 times. And we're going to have x to the 2nd on the outside. And what's left underneath is an x to the 1st. Whatever was left over from that gets put underneath. So from this comes that number, and then whatever was left over gets left underneath. Now we'll talk more about that in a second, okay, because that kind of gets confusing. So, for example, let's do another one. The cube root of a to the 6th, b to the 9th. Now I don't have to have numbers, I could just have exponents, so let's look and see what that one is. If I divide both exponents, I have 6 divided by 3, which is 2, so that divides evenly. 9 divided by 3 is 3, that divides evenly, b to the 3rd. So my final answer, a to the 2nd, b to the 3rd. No square roots or cube roots left. One more like that. Let's say the cube root of a to the 12th, b to the 17th. Now, here's the thing. This is what I was talking about earlier. 17 does not divide by 3. A does. 12 divided by 3 is 4, so I would have a to the 4th on the outside here. But 17 does not. So think of the next highest number that's close to 17 that actually does divide by 3. And that would be 15. So b to the 15th and b to the 2nd that's left over, multiply and add to 17. So remember, when we're multiplying our bases, we add our exponents. So if we write this kind of as a multiplication piece, we have 15 from the 17, and then what's left over is 2. So the only one that's going to be able to divide is the 15. 15 divided by 3 is 5. So b to the 5th goes outside the radical. But what's left over needs to go inside the radical, and that would be the cube root of b squared. That's how I do it in my head, okay? So just make sure that you're able to do all of these things, and you're able to kind of piece all of it together. Now, you could have exponents with you can have variables, you have numbers, you can have negatives, you can have all the things. If it's a cube root, you can have a negative. If it's an even root, it can't be negative underneath, okay? But all of these problems, that's how you would simplify all of your radicals, okay? We can do one more like this. We can do the cube root just to show you, because I have I think I'm going to have some people that are confused right now, and I want to make sure that you are good, okay? So let's say I have the cube root of x squared and y to the 7th. So just working on the variables, I feel like you probably got the numbers down, but x to the 2nd. Now 2 does not divide by 3, so automatically I know that I'm going to have a cube root with x to the 2nd underneath. Now we see if we can split the y's. So the 7 doesn't divide by 3, but 6 does divide by 3. And what's left over? 1. My computer's slow, I'm sorry. 6 divided by 3 is 2. So that y to the 2nd goes on the outside. The 2 goes on the outside because I've divided it evenly. But that y to the 1st stays on the inside. And that is how I simplify it. So you kind of have to think about it in stages. Hopefully that last example cleared some things up for some of you if you're having questions. Otherwise, work together on this assignment because it can get kind of messy. But that is all for this lesson on simplifying radicals.